Okay, you're on.
Okay, yeah, so thank you for the invitation to talk. Because I seldom give technical talks. Now all the talks that I'm asked to give are very high level talks, you know, this and that, you know, this. Okay, so this is, I'm going to talk about what I'm interested in today. I've given a similar talk before somewhere else, around this area. So the talk today that I put is actually, there are two title: optimization with big data. So where I'm coming from is that I started out working on optimization. Of course, optimization, there are two classes. One is continuous optimization. The other one is actually discrete or combinatorial optimization. So I started out my research doing a combinatorial optimization basically on graph structures and so on. Then I moved to machine learning and so on. So today I'm also looking at both these areas, because essentially problems in machine learning are actually formulated. If you look under the hood, it's actually an optimization problem. Okay, whether it's complex or non-complex, it's still an optimization problem. So what my aim for today's talk is actually to motivate you to look into, because all of you are doing some sort of machine learning somehow, right? You may not be directly interacting with the optimization issue behind, but I'm trying to motivate you to look at the problems in machine learning from the perspective of optimization. Because why is that? If you look into many basic research in machine learning, okay, a lot of fundamental research and advances are actually made in light of how you actually how you formulate the problem and how you solve the optimization problem. Okay. And what I also want to illustrate to you is that I use a very simple example. Okay, I just use the example of a linear regression. Some of you like to use a linear regression. Because the fancy one today could be ridge regression or whatever it is. So what I want to do is I want to take an example from there, okay, and look at two challenges. One is a challenge of the data volume. Okay, so of course linear regression has an analytical solution. Computationally, typically for some of the optimization problem, you use things like gradient descent. Okay, that is the plain vanilla one. Okay. So in this talk, I try to motivate why we run into trouble if we use a gradient descent for large volumes of data, and how we can solve that issue using stochastic gradient descent instead of just gradient descent. And there are other people who are actually looking at distributed data. Okay, because as you know, there are many methods of machine learning already out there. Okay, and then you look into Hadoop, which has some distributed machine learning library called Mahmoud and so on. Why the trouble with machine learning is that because most of the optimization problems optimization solution that we have works with the assumption that you can see a global information. Once your data is distributed, then distributed optimization becomes a tough thing, right? And then you come with distributed protocols and so on. So this is what I want to do today, and if you are try to motivate you and open up your eyes to some of the issues. Okay. So first, we look at machine learning from the perspective of optimization. Are you familiar with this? If you have seen it before. Okay. This is essentially, if you work in machine learning, or at least look at some of the formulation, this is the least squares regression problem. You have your loss function here, and you have your regularization term here. So this is L2 regularization. Okay, so similar to your ridge expression. So what we do is that you take the loss function. Essentially, you take actually the difference between the true value, or the ground truth, and the W here is actually what we have learned, the coefficients that we have learned. T is the transpose operation, and x is actually the vector, the data, input data. So basically, you take the loss function, okay, average it over n, and of course, this may not be necessary actually, okay, but you may put it there for regularization purposes. So essentially, what you want to do is that you want to minimize the loss, right? Okay, you want to minimize the loss, and minimize the loss with respect to the coefficients that you get, which is basically a vector of real numbers with dimension d. So, okay, but most of the time we don't actually worry about this because this is already formulated in this way, right? And so essentially, either you are working with regression or you are working with classification. This is the standard form. Okay, but if you are working with classification, okay, this what you do is that you still have regularization, but you just specify a loss function. This is a generic loss function. It doesn't tell you anything. Okay, just substitute this. So the loss function in the case of regression, least square regression, is of course this one. Right? You have. Do you know of any other loss functions that we use? Yeah, for classification, you have things like the hinge loss, H-I-N-G, hinge loss function. You have things like force entropy and so on. So essentially, what you are doing is that you are actually fixing the loss function here. But the only thing that you have to be a bit careful is that the properties of the loss function, because the properties of the loss function very much influences what you use for your as your solver. Right? So basically, your classification problem will actually do something like this. So the only difference is that what do we fix for the loss function and what is the regularization term that we are going to use. Okay, so of course the most common one is your L1 regularization. L1 regularization is also called RESO. Some of you have looked at it. So if you use L1 regularization, what it does is that it will push most of the weights to zero. If you use L2, with L2 regularization, it will actually push most of the weights to a very small number, not zero. Okay? And if you have used ridge regression in R or whatever, so ridge regression in R actually uses the L2 regularization, but in the what it does is introduce a new variable and multiply that variable with the identity matrix. So it's called ridge because the identity matrix has a diagonal one, so that's why we call it ridge regression. So, and now this equation doesn't tell you much unless you actually see what's inside the loss function. Okay. Now, any questions so far? I'm going too fast or? Okay. Okay, so let's look at the first challenge. Too many data instances, computationally expensive. So one of the so let me illustrate this by first looking at what we do for gradient descent. Right. So let's formulate the cost function for this square linear regression. Okay. So I just simplify what we have seen earlier on. Okay. So this is of the same form as this one, but without the regularization term. So just to understand basic properties, we throw away the regularization. So common algorithm is called gradient descent. Who has not heard of gradient descent before? Okay, so now because we want to now this is linear regression is a nice problem because it's what we call a convex problem. It's a convex optimization problem. So now before going further, I think I should explain what is convex and what is non-convex. In convex optimization, there are two kinds. Right? One is convex, one is strictly convex. So if you have in your house, when you use a bowl, right? Okay, a bowl is actually convex, right? Okay, so for a convex problem, you always get the That any optima, I mean, you only have one optima, right? So that is a global optima. Okay, right? So, but if you have non-convex, the surface of the function is actually, it has a lot of hills and valleys and so on. So most of us like to actually look into deep learning and so on. So unfortunately, deep learning, the optimization problem for neural networks, is actually is non-convex, and people are trying to understand that from the viewpoint of physics. So let me just go to gradient descent. So if you imagine, so now I'm trying to explain how the optimization goes. Right? So can you imagine your bowl, right? Okay, can you imagine your bowl, and you imagine yourself as a small ant on the surface of the bowl, right? Right? You have a big bowl. You imagine yourself as a small ant on the surface of the bowl, and your objective is actually to move down to the bottom of the bowl where the minimum is. Okay, so for a very small ant on a very big bowl, okay, you can't see the end, right? You can't see the bottom part, right? So what do you do? So this is exactly the so what is the heuristic that you are going to use? You know that there's a gradient, right? There's a curve, there's a gradient. So what you want to do is that you want to follow the direction of the gradient. Okay. Of course, if you are greedy, then you follow the steepest gradient. Okay, in that particular direction. So this is the. So what you do is that then you take steps, right? So you have a goal, right? You keep on moving and you are taking steps until you find the optima. So to cut the story short, actually, so what you do is that for each weight or for each coefficient that you have, you actually compute the new value, okay, by adding this term here. So this is the whole value plus this is the learning rate alpha here. Okay. If the learning rate is too big, you jump too much, you end up in a different place. Okay. Now for this equation here, for this LS here, what you need to do is that because you need to compute the gradient, right? So if you have multiple regression, that means you have more than one variable. So what you can do is actually to compute the partial derivative. Okay. And the approximation of that is actually this is xji here. This is actually the approximation of the partial derivative. So it approximates the gradient. This is coming from the loss function. Okay. So this will give you the next step. Okay. So this is essentially how gradient descent works, and this is the in fact the algorithm is so simple. You do this until convergence, whatever convergence may be. Okay, you define it, right? So now, so in terms of with reference to big data, so the trouble is you look into this one. If you look at the summation here, you see that for gradient descent to actually take one step, right? Conventionally or traditionally, you have to. This summation means you have to look at the entire data set. This is how the original plain vanilla gradient descent works. So if you have 1 gigabyte of data, you have to go through everything and then you can take one step. Of course, you have to approximate the gradient. So this seems to be the issue. So that's why in a lot of toolbox that you use for big data and so on, you seldom see gradient descent. You always see SGD, right? Stochastic gradient descent and so on. So this is just to motivate you. If you want to do research, perhaps there are many areas that you can see some of the things that can be, you run into issue with the big data, and then you can actually look at how to actually solve it. Okay, so adding some stochasticity actually helps speed things up a bit. Okay, so our concept is that we want to look into the whole data before we actually make a step in when we actually do gradient descent. So what we want to do is that, so how do we add in the stochasticity for this one? So first, randomly shuffle the data instances. Okay. So effectively, randomly shuffling the data instance is more or less similar to just randomly picking something out. Okay. So step 2, So what you do is that for each step, right, you update each step by just looking at one data point. Okay, but of course there is a trade-off. No? Okay, nothing looks as good as it is. There is of course a trade-off. It is fast, but you may take longer iterations to converge, and you have to really control your step size. Okay? Because that will influence the direction that you want to go. So the direction that you want to go will be influenced by the sign of the gradient. Okay, so in SGD you can just take one step after looking at one data instance. Okay, so this actually makes it much faster. So this is actually just a small example. Okay, right? And so hopefully, after this, after you have found out about this, you can think about, some of the other algorithms, machine learning algorithms that you're actually using. Do they suffer from such issues also, for example? Right? Any questions so far? Of course, there are many variants of gradient descent. And the last part of the talk, this is still centralized, right? So this assumes that all your data sits in one place, and it assumes that you can compute the gradient based on whatever constant you want. Okay. But of course, a distributed system is not the way. So there is recently a very interesting paper that came out from Berkeley. So at the moment, I think all of us know that Hadoop is the platform for distributed processing, but it's a MapReduce well suited for machine learning algorithms in a very distributed way. So this is not my answer, that's why I make it in italics. Okay, this is one of very interesting paper that I'll show you the reference later on. So they found out that it's probably not. So they have come up with the alternative abstraction. So this is a recent, also recent, 2014. Okay. Instead of using MapReduce, they introduced a new thing called all-reduce abstraction. Yeah. But it's a common name also. Common name. They may not be the same person.
It's the same thing.
So what is good about this is that it allows the parallelization of gradient-based optimization algorithm. Okay, by using the all-reduce structure. So basically, there's a tree structure in the setup. Okay, so what the communication actually goes up to the root and then comes down again. So at any point, the aggregation will be done. For example, this is actually just calculating sounds. So the global sound will be transmitted down. So I didn't go actually further into this. You want to have a look at it if you want. Actually, quite a lot of people are actually looking at alternative structures instead of MapReduce. So that paper happens to be in Journal of Machine Learning Research. So those who are, if you are doing research in looking at MapReduce and so on, I think you should look into this paper. And of course, people like Langford and so on are well known in the machine learning community. If you are going deeper into optimization and so on, there's a paper from IEEE Signal Processing Magazine on complex optimization for big data. And there's already an algorithm called HOG, WILD, which actually is a parallel implementation of SGD. So that is already there. Okay, that's already there. I think it's mentioned in one of these papers here. So this is just a short talk. I'm not sure whether I went too fast or what, but as I mentioned earlier on, my aim is actually to motivate you to look into machine learning from optimization perspective. And fortunately for us, many machine learning problems are actually convex problems. Your linear regression is convex, your SPM is convex. Okay. Neural networks of optimization is not convex. And one of the interesting bit that I've seen recently is that because now you ask, because most of you are also doing deep learning for popular reasons, there's a recent result that came out that says that they asked the question: if you run a multi-layer deep network many times experimentally on the same, what you do is that they are observed that more or less every time you run, you get more or less the same results. So now they're actually trying to explain why is that so from the optimization algorithms that going on behind. And we also try to see whether there's something in physics called the spin glass theory. So they're looking at whether the spin glass theory can explain the behavior of that particular structure. So it's actually very interesting to look under the hood. For that one, not just applying now. Of course, applying when you see the results good, then you're also happy. But we want to go further and see what's going on behind. Okay. So is there any? This is just a short talk. I can give you a talk next time. Questions that students want to ask?
I wanted to add as well that if you go beyond progressive grading, there's another one called batch grading.
Yeah.
Where it becomes better and it's a very similar form to the batch that you process deep learning. What they do is they break it down into submodular batches, and so it converges faster and also more efficient because you have a deep learning level that is very large, then you need to do all these batches. So I think that should be the state art compared to the
so this one is just to illustrate the issues that we face when we go for technical. Many other stochastic gradients, gradient-based algorithms that we use on batch and go to the next. My objective today is to actually let you see, one of the key things or one of the key issues that can arise if you just use such things. So you can approach it from three ways from so I know John is looking to this because he can do comment on number one. I'm not sure if everybody any other questions from the student? I'm not sure what you're working on. We want to have some discussion now on some of the technical stuff that we're looking at.
Okay, so the talk has ended, right?
Yeah.
Okay, then I can stop the recording.